Okay, I guess it is 2 o'clock, even though the clock doesn't seem to agree with me. So, welcome back for the afternoon session. So, we'll have the first talk in the series by Professor Indira Chatterji from the University of Côte d'Azur at Nice. And her talks will be on property T, median spaces, and cat-0 cube complexes.
All right, thanks a lot. Thanks a lot for organizing this and being here, showing up to listen to property. Oh, this is loud. Why is it so unpleasantly loud? I am loud without a speaker. No way. Okay. All right. So, So what I would like to talk about is, in fact, my try to understanding the world of finitely generated groups. And see, I'm from Switzerland, so I like to put things into boxes and order things and classify things. So finitely generated groups, you cannot classify. This is better? You think so? Yes. Oh, that's the other pocket. Okay.
Thank you.
All right, is that better? Less loud? Okay, so you can't classify all finitely generated groups because there are too many. Finite groups have been classified, but somehow I don't understand those well enough. So, okay, so my view of how the world of finitely generated group is the following. In my view, in my classification, there are groups with property T here. There are groups that called anti-T, or also atemmenable, and there are groups that are neither. And so property T, in fact, okay, I'm going to give you a non-standard way of doing this classification via median spaces. So I'm going to take a metric space, and I'm going to assume it's geodesic, meaning that between any 2 points, I always have at least one and maybe more geodesics joining those 2 points. And I'm going to denote by I of xy is the set of t and x such that the distance between x and t plus the distance between t and y is equal to the distance between x and y. So those are the set of points on a geodesic between x and y. It's called the interval. Between x and y, and xy are 2 points in x. And I'm going to say that x is median if for any 3 points x, y, z, then the triple intersection of this interval is reduced to a single point. Non-empty, and it's reduced to a single point. So the first examples I can look at, well, is R, the real numbers, with the usual distance. And you can, and so this point M is going to be the median point of X, Y, and Z. So the first example is R, and if I pick 3 points, one of them is in the middle, and that's going to be my median. And you can see that just because the interval between x and y is going to be that, the interval between y and z is going to be that, the interval between z and x is that. So you can see that this is the only thing you can find in the triple intersection. The other example is trees, right? Because if you take 3 points, x, y, and z, then again, the only interval, the only geodesic is the interval, and each time you have only one geodesic, and this is the point, this is the median, and you can also have, you can also have, let me just write R2, now with the L1 metric, because then if you have 3 points, X, Y, and Z, that's the interval now looks like this, and like this. So I have one triple intersection point. Those are median spaces. I will talk about median spaces more. For those who know what that is, another big class of example of median spaces are CAD0 cubical complexes, where I throw away the CAD0 metric and I replace it with some other metric. So, all right. Now I see that I'm given an introduction to property T with a bunch of people that know property P much better than me. Anyway, so it's a non-standard introduction. So, okay, so right, so this is the definition of a median space, and for a few minutes, I will define G has property T. It's a non-standard definition, so you'll see a more standard one in a few minutes. If any action on a median space any isometric, all my actions are isometric. I don't know how to deal with non-isometric actions. Has a bounded orbit. And I'm going to say that G is anti-T if it admits a proper isometric action on a median space. And then you can be neither. You can admit an action on a median space that has an unbounded orbit, but be a stabilizer. For instance, this is the first. It's pretty easy to see that any product of two median spaces is again median. So if you take a property T group and you cross it with, you make a direct product with an anti-T group, you will get something that's neither, because you will get an action in a median space that has an unbounded orbit, but that will have a huge stabilizer. Okay, so yes. Yes, it has to be exactly a singleton, non-trivial, non-empty, 1 point. And for the story, people were studying median algebras in the 50s. They were studying it without the metric, really just as just with this median operation that satisfies some property. I will do the thing totally in a totally geometric way. And this is a non-standard definition of property T. I will start with a standard definition of property T in a few minutes, but I will use this way of looking at things to say, well, this is how I separate my worlds of groups, with some groups that have property T, some groups that are anti-T, and some groups that are neither. And we also saw quite a few groups today. We saw hyperbolic groups. So hyperbolic groups kind of are somewhere here. Right? You can be property T, you can be not property T, you can be neither. So we'll start filling in. So this is hyperbolic. And so this here is well, actually I'm wrong. That should be like this whole line. There's finite groups. because only finite groups can both act properly on a median space and have a bounded orbit. So those are finite groups. Here, so what did we see? We saw F2. F2, we'll see that F2 this is a hyperbolic group, and we'll also see that it acts properly in a median space. Actually, it is itself a median space because it's a tree. You have a bunch of things here. You have surface groups, and you have more generally lattices in SO and 1. And those are all examples of CAD0 cubical groups, which I will put here. So those are going to be CAD0 cubical. So groups that admit geometric action on a CAD0 cube complex. In particular, the action is proper. That's in the definition. So it's a proper action in a median space if you accept that CAD0 cube complexes can be viewed as a median space. Right. So those are CAD0 cubical. There's another important class of groups that we know and that I should have. So there's another important class of groups, which is amenable groups. And amenable groups would be somewhere here. I will discuss amenable groups. I'll discuss most of the words I say now during those mini courses. This is not prerequisite. This is just me saying where we're going. So the intersection between amenable and hyperbolic, what is it? It's Z, more or less. So virtually, it's Z. The intersection between amenable and CAD0 cubical is virtually Z to the n. Everything I write is true up to finite index. What else? So here we have, okay, so this is amenable groups, and here we have whatever is polynomial, well, here we have a bunch of polynomial groups that are non-abelian. Anyway, we have a bunch of stuff. So what do we have here? Here we have a hyperbolic group that doesn't act on a CAD0 cubical complex, but that still act on a median space. That would be lattices in SU and 1. And here, among the property T examples, are lattices in SP and 1, and there is, I think it's F4 minus 20. It's one of those exceptional guys that exist. Okay, and if you want to create hyperbolic groups that are neither property T nor amenable, you take one here, and you make a free product. If you make a direct product, you're not hyperbolic anymore. So you can take some lattice in SON1 with SPN1. It's F4 minus 20. It's a rank 1 Lie group that you can think of as the isometry group of the hyperbolic plane over the octonions. Right, so what else do we have? We have in the property T place, I haven't written much. So the important example are SL and Z for n greater or equal to 3. SL2Z, you're going to find here. And all lattices in higher rank Lie groups. And what else do we have? Yeah, we have, we're missing a few famous examples. Oh, yeah, so recently we have out Fn for n I'm not sure. Greater or equal to 5 for sure. Maybe 4, I don't know. Greater or equal to 3? Okay. I'll trust you. Okay, what else? Yeah, so in the neither category, we can take I told you can take somebody here, and make a product. You can also make some semi-direct product. Here is a very famous semi-direct product where you have SL and Z that acts on Zn just by matrix multiplication. And you get a group that is neither property T nor AT amenable. Okay, any question about my picture, my world of groups? Yeah, I guess I should have another category, which is question mark category. One that we don't know where to put is mapping class group of a closed surface. If you Google it, you will see that somebody think that it's in the not property T category. That proof is not totally vetted by the math community for the past 20 years. So, okay. So I think mapping class group we don't know. Right. So that was my introduction and motivation on why to, that's my introduction and my motivation on why to study property T. And now I will start with a more classical definition and the original Kashdan's motivation to study property T. So property T was introduced in the 60s by Kashdan. And his motivation was the following. So the classical motivation is the following. We all know that SL3Z or SLNZ, okay, let's say SL3Z, is finitely generated by elementary matrices. So yeah, so I'm sure you all know that. If you don't know it, it means that you have taught it in first class. When you teach row reduction, this is actually what you do. When you do, each time you do a row operation, you multiply by an elementary matrix. So EIJ, and it has one in the, so that's my first elementary. So that would be E12. And then you can check that if you do E12 to the power n, you get an n here. And when you multiply by one of those elementary matrices, what you do is you add the n multiple of a row to another row. So when you do your row reduction, really what you're doing is you're finding a path of elementary matrices between the identity and your matrix. Okay, so so that was well known. And if you have, yeah, right, okay. But if you take gamma, a discrete co-compact subgroup of SLNR, yeah, so just this is a subgroup of SL3R. And it's a discrete subgroup that's not co-compact, but has a finite volume. So so when I say semi-simple Lie groups, if you don't know what it is, you can just think SL3R. So this is a locally compact group, so it has a Haar measure, and when you look, and SL3Z has a fundamental domain for this action on SL3R that has a finite measure. So so if I take G, a locally compact group gamma, a subgroup of G is a lattice if it is discrete and finite covolume for this hard measure. Okay, so if you have if on top of having a finite covolume, your subgroup is co-compact, then it's easy, it's standard to see that it's finitely generated. It used to be called Milnor-Swark lemma when I was studying, and now it's called the fundamental lemma. That's okay, I think that both Milnor and Swark had a good job. Okay, so now it's called the fundamental lemma. In the fundamental lemma says that that gamma is finitely generated as soon as you have a co-compact action on a connected metric space. If gamma acts on X connected geometrically. Right, because here is your ambient group or space, and then you have gamma, which is your co-compact, discrete co-compact subgroup. So what you can do is you're going to write X as the union of, you get a covering. Since it's co-compact, you can cover X is going to be contained in a union of balls centered at elements of your lattice. Right, let me just pretend X is G. You can do the same thing with a metric space with an ambient group. It's slightly easier because you don't think of an orbit, but it's more or less the same idea. So what you're going to do is you're going to take S as the set of S in gamma, such that the ball of radius x0 r intersect. So this is R big enough to cover the fundamental domain. And then you're going to take the elements that move the ball not off of itself. So and what you do now, you take gamma in gamma and you want to express it with finitely many elements in S. So you're going to look at the identity and, oh, I'm here, I'm taking the identity. So it's all covered by balls. So I'm going to take gamma here, the identity. I'm going to take a path, which I have because I know that the space is connected. This is compact, so there's a finite covering of this path, and that gives me my finite path going from the identity to gamma. Cover the path between the identity and gamma with balls and get the word in alphabet S, like this. Okay, so now we know that for this particularly nice lattice, it's finitely generated. For the co-compact ones are finitely generated, but there is a bunch of other lattices that you get with number theory considerations that you can build. So that's a huge class of groups, very interesting groups, kind of natural, but we didn't know if they were finally generated or not. And so yeah, that's the question, is what about other lattices? And so it was open to know whether they were finally generated, and Kashdan answered by saying yes, because of property T, which he introduced. And yeah, so that's what I'm going to talk about now. I'm going to talk about Kashdan's definition of property T, and how from property T you deduce finite generation. Okay, right. So for a little while, I'm going to do the definition for G locally compact, second countable, but in my head, G is always discrete. So hopefully I'm not going to say too many wrong things. So I'm going to take, yeah, okay. So for the part that I'm going to describe now, I based it on Kashdan's original paper, which is 3 pages. So I urge you to read the 3 pages. He was 17-year-old when he wrote it. So my knowledge of 17-year-old people, you always should be very careful when you listen to what they have to say. In this case, it's very interesting and very insightful. So maybe we should listen to more of what the 17-year-olds say. I don't know. Okay, so right, so G now is going to be locally compact, second countable. And, right, okay. So I'm going to define G hat, which is the space of strongly continuous, irreducible representations going from phi to the unitary operators of a Hilbert space. So what does it mean? So, right, so unitary operators, those are just the set of U from H to H such that U star is the identity. It also means they have norm 1. The operator norm of the norm of pi G that I apply to Xi is the norm of Xi. And strongly continuous is not very interesting if you're in a discrete group, but it's useful in general. So strongly continuous means that if you think of the map from G to H, you fix a vector. You fix Xi and H, and you look at the map from G to H that maps G to pi G Xi, you want this one to be continuous. So if your group is discrete, then this condition is void because everything is continuous. All right, and then this is contained in G twiddle, which is all the representations, not necessarily, so all strongly continuous unitary representation. And there is a subtle consideration on G twiddle that it's not necessarily a set because there's too many Hilbert spaces. So, but anyway, today nothing so subtle will happen. So okay, so this is, at least this I'm sure is a set. We're going to put a topology in it, which is called Feld topology. on G hat and G twiddle. So how do you, yeah. So how do you, so we're going to define the topology using bases. I'm going via a basis. So a basis for the topology, so I'm going to take a representation, and I'm going to say, and for the basis, I need epsilon greater than 0. I need a bunch of n vectors in H, and I need K contained in G compact. And I'm going to say that representation pi prime H prime belongs to the epsilon psi K neighborhood of the representation pi, if and only if. So sometimes I write pi, sometimes I write pi comma H, depends. But it's really the same thing. If you're unsure, you can ask. Okay, so when is it that you're going to say that this representation is close to this other representation for those fixed data? It means that you can find other vectors prime and other vector in H prime such that, in fact, such that the representation pi will mimic what the representation pi prime can mimic what the representation pi can do on this set. So it means that pi g ci is not very different from pi prime g ci prime is less than delta for all g in K. Right. So that's what it means for this representation pi prime to be in the neighborhood of the representation pi for this kind of window. So this I think of this like kind of a window where you look at what pi is doing, and you're going to find something that's more or less doing the same thing on that window. And right. So this is the file topology. All right. So what can we find in G hat and G twiddle? What can we find in G hat and G twiddle? I'll give you the few examples of unitary representation. It's a big jungle of stuff that are not very well understood. And but there's a few representations that we know are there, that are always there, and that are reasonably well understood. The first one being the trivial representation. So what can we find? Yeah, the n need to be the same. Yeah. Yeah, well, this up to permutation, you don't really care about the I. No, all possible Hilbert spaces, yeah. Infinite dimensional most of the time, but you're allowed finite dimensional, but most of the time it will be infinite dimensional, yeah.
What does via basis mean?
So topology, you need, in order to define a topology, this is the basis of the topology. So it means that you get the open set with intersection and stuff like this from those.
And are the xi i's supposed to be related to xi i's, xi I primes related to
No, not really, because this is a different Hilbert space. It's not necessarily, they don't necessarily live at the same place, but you can find a set on which both representation will do the same thing. Yeah?
Are we also considering the
Yes, yes, the representations are up to equivalence. Where do I write this? Yeah. Yes, we're considering, we consider the representation up to equivalence, where pi is equivalent to pi prime if there exists a map A, which is from H to H prime unitary, such that pi prime G is A pi G A inverse for all G in G. So they're intertwined. Okay, oh yeah, and maybe I'll tell you what, and you're going to say that it's reducible, if you can find V that's in H, but not all of H, such that pi doesn't move V off of itself. And in this case, you will say that pi restricted to V is a subrepresentation of pi. And okay, so I was here, what can we find in G hat and G twiddle? The first one you can find is the trivial representation. That goes to C, which is, and the unitary group of C is S1. So what this will do is it will map everything to 1. So that's the trivial representation. And then I can give the definition of property T. A group G has property T so this is Kashdan definition. If and only if the trivial representation in G hat is isolated for the file topology. Okay, so that was that's Kashdan's original definition, and so in his paper he puts property T without parentheses, and I've always been told that you put property T with parentheses because it means that the trivial representation is isolated, and then to my surprise, I went to Kashdan's paper and he didn't have the parentheses. So I looked around. The first place where I saw the parentheses was in Margulis' book. So maybe that was Margulis' explanation. Okay, and right. Okay, I'll come back to this definition because, so okay, so the standard reference for property T, it's now Valette de la Harpe. First, Valette and de la Harpe has a small book in French, and then now there is a Becca Valette de la Harpe, a much bigger book that's very complete. That's a very fat book on those 3 pages paper. So most of what I'm telling you comes from there. And okay, so what else can we find in G twiddle? We can find other representations, other unitary representations. So now it's going to be something that is in G twiddle and not in G hat. The first very important one is the regular representation. You map G to the unitary operator on L2 of G. So if G is discrete, it's just little L2 of G for the counting measure. But in general, you need to use the Haar measure to do that. And how do you do that? You map G to lambda G of Xi. So Xi is an element in L2G, so you need to understand Xi, you need to feed it an element of G. So let's call it X. So that's going to be Xi of G inverse X. So if Xi is an L2 function, what the regular representation will do is will displace this L2 function. So it's obviously unitary, because if you displace it like this and then you displace it back, the adjoint is the displacement by the inverse. Okay, and there is, oh yeah, so, and there is also the semi, so this is the regular representation. There is also semi-regular representation. You take a subgroup of G, it needs, I think, at least to be closed. And you're going to look at lambda. Maybe I should call it lambda GH. That goes from G to the unitary operator in L2G of G mod H. So now you have functions that are defined in cosets, and you're going to move around this function defined in the coset. It's defined in the same way. It's defined in the same way. And so let's now, for those unitary representation, let's just look at, let's just make a quick remark. If you look at the vector, the Dirac mass at the coset H, so this is the Dirac mass at the coset H, that's an element in L2 of G mod H, and is going to be H invariant. For the regular representation. And another remark is that for the semi-regular. And the other remark is that the regular representation never has an invariant vector unless the group is finite. Because, so here you have G, and L2G has to go to 0 at infinity if G is infinite. If it's finite, you can do whatever you want. Oh, unless G is compact, sorry. So finite if G discrete. Yeah, thank you. Right, so, but in case of a discrete infinite group, since you have to go to 0 at infinity, you cannot be invariant, meaning that it means that when you move it around, it's always the same. The only way to be invariant is to be constant. And you can only be 0 if you're constant on an infinite group, and L2. Okay, so those are the important remarks. And where am I? Okay, yeah, so just, I think I'll erase that now that I have a good eraser. I'll keep my picture, that way you can add your groups, your favorite group you can add in the picture. Oh, this eraser is so much better than the little erasers. Okay. Oh, chalk in my hand. Okay, so I'm going to say that maybe a few more terminology. Yeah. So I'm going to say that P, so I take a representation rho and I close it for this Feld topology. And I take a representation in the closure. I'm going to, if we say that pi is weakly contained in rho. And okay, and then I'm going to make a few more easy remarks, which is that if P is irreducible and pi has an invariant vector, then pi has to be the trivial representation. Right, because otherwise this invariant vector is going to give you the subspace you can split on. So pi in a neighborhood of T no, it's not. That's another remark. I take a pi. Now pi is not necessarily reducible. It's another remark. I take pi in a neighborhood of T. What does it mean? If I go back to the definition, it means that for any compact subset and epsilon greater than 0, there is psi in H such that pi g psi minus 1. So 1 is just because I'm looking at the trivial representation and I take a norm 1 vector. So this has to be less than epsilon. Right, okay. So that's a reformulation of being in the neighborhood of the trivial representation. And so now if we compute pi g psi minus psi, the norm squared, this by definition is the inner product of pi g psi minus psi with pi g psi minus psi, okay? And if I make the computation, I get that this is bounded by 2 times 1 minus the real part of pi g psi with psi, right? So if this is small, the real part is going to be small, and pi close to the trivial representation means we can find a vector psi in H such that pi g psi minus psi squared is smaller than epsilon. I can even remove the square. For any g in K. And C is norm 1. And those are what are now classically called epsilon K invariant vectors. So psi is an epsilon K invariant vector. Right, so, And so that gives a rough formulation of probability T, which is which is that a group has probability T, G has T, if any representation with almost invariant vectors has an invariant vector. And this is the definition that you will find, for instance, in the Bécard de la Valette. Right. Okay, so an easy first consequence is, or from an easy first fact to see from the definition, is that compact groups have probability. Okay. No, maybe I'll do compact groups. Okay, compact has probability. So how do you see that? You take epsilon small and G is equal to K, and you want to show that that the V epsilon x k neighborhood of the trivial representation is reduced to the trivial representation in G hat. So you take pi irreducible and you have x that satisfies that pi g x minus x is less than epsilon. Here you have your representation, you have your x, and your representation is going to move x not very far from itself. So the fact that epsilon is small, it means that if you look at y, which is the average of all the stuff you moved, you get non-zero. So you get a non-zero vector, so you get your non-zero invariant vector. So y is an invariant vector. So for pi, which was irreducible, so pi is equal to t. Okay, so there's no, it's not an if and only if, fortunately, otherwise we'd be doing finite groups. There is a partial converse. Well, there is something which Kajdan called a partial converse, which is that if G has probability, then G mod the abelianization is compact. Yes?
Sorry, I was still.
Yeah.
A small neighborhood, and you want to say.
Yeah.
You know there is a pi.
Oh, I take something irreducible, which is in this neighborhood, and I show it can only be the trivial representation. And so I take something irreducible and I produce an invariant vector for it. Yes, yeah, because I assume it's in the neighborhood of the trivial representation, and that allows me to produce this invariant vector. Okay, so it's not an if and only if, but if you have property T, then the abelianization is if G has T, then G modulo the commutator is compact. But I'm not going to prove that. What I will show you is that if I have an amenable group, then it never has property T unless it's finite. So, and that's my pretext to give a definition of amenability. That's okay, I still have 15 minutes for that. Okay. So, amenable intersect T is compact. But today I'm going to do finite. But in the locally compact case, it works the same. So we have some groups that have property T. Today I'm not going to be able to show that SL and Z has property T. I will give a sketch maybe later. Not totally even sure that I'm going to do it. Yeah, I'll give a sketch of the proof for that. But now we're going to see that amenable groups never have property T unless they're finite. So what's an amenable group? Okay, recall, but maybe you don't know it. So amenability, you have a ton of equivalent definitions. G amenable, if and only if, for any F contained in G, okay. Let me just do it for G discrete. For any F contained in G finite, for any epsilon greater than 0, there exists U contained in G finite such that Fu symmetric difference with U divided by U is less than epsilon. So this is Fellner condition. This is Fellner condition, and what does it say? So F is a finite, so think you're in Z, and F is plus or minus 1, then you're going to find a large set. If you take, for instance, 0 to n, so Fu is going to be minus 1 to n plus 1, and when I do the symmetric difference with U, I just get 2. And so if I take U that's large enough, I can make this quantity as small as I want. So basically, amenability tells you that each time I give you an epsilon, and each time I give you a finite set of moves, I can find a large set that doesn't really see those moves up to epsilon. Okay. Yeah, so this U depends on F and epsilon. Okay, so, right, so now we can go back to property T, and you take F is your compact set in the definition of property T, and epsilon, and you take psi is 1 over, is the characteristic function of U, but normalized to have norm 1. And this is an F epsilon invariant vector for the regular representation lambda, because if you try to compute lambda s xc minus xc squared, so you're going to have to sum that over g and g of xc S inverse G minus CG. And this, when you plug in the values, is exactly that. I mean, it's bounded by that because, yeah. So this is the sum over G in FU symmetric difference with U divided by U, and this is exactly less than epsilon. So this shows that if you have an amenable group, you can find almost invariant vectors. But we have no invariant vector unless the group is finite. So imply if G has T, then it has to be finite. Okay, and I promised you that, oh, good, that I'm going to give you finite generation. Now I'm going to take G, which is a countable discrete group. So theorem. So this is all Kazhdan. Gamma countable discrete has T, then gamma is finitely generated. Okay, how do we do that? So to prove that, you start by enumerating gamma. Which you can do because we assumed it was countable. So then you're going to find a sequence of subgroups. They're all subgroups in, so they're all subgroups in gamma, and you want to show that at some point gamma n is equal to gamma. In fact, what we're going to show is that at some point gamma n is a finite index in gamma, which is good enough. So enough to show that gamma n finite index in gamma for n large enough. So we're going to look at lambda, a semi-regular representation. I'm going to call it lambda n, goes from gamma to the unitary representation of L2 of gamma mod gamma n. And we want to find an invariant, and so it's enough to find an invariant vector there. For that semi-regular representation, right? So we're going to take K compact, so finite in my case. And right, so you take K finite and n large such that K is contained in gamma n. But if you do that, you will have an almost invariant vector. Then it's an almost invariant vector because it's a K invariant, vector. Then eta, which is the characteristic function of the coset gamma n, is an almost invariant vector because it's K invariant since it's gamma n invariant. Right. So now we assume that it had property T. So now you have an invariant vector. Which means that gamma mod gamma n is finite. And hence gamma is finitely generated. Okay, maybe since I have 5 more minutes, I'll give you another definition. And make a few remarks, maybe. Yeah. Here's an important remark. Yeah. An important remark is that if G has property T and you take a normal subgroup, then the quotient has T as well. Because indeed, this map is continuous, especially if you're in the discrete case. So the map from G hat to G mod H hat also, and so preserves isolated points. Okay, so that's an important. Yeah. So yeah, H closed. G mod H hat. Oh, the map is in the other direction. Thanks. Yeah, so H needs to be closed. In my case, everything is discrete. Yeah. So, but this is a very important remark because it means that as soon as you're subject to Z, you're done. You can't have property T. So that rules out a big class of groups. It's an easy obstruction. It's not the only one. There's a bunch of groups that have no surjection to Z and don't have no surjector and don't have property T. Oh, there's too many negations for that time of day. Okay, I think I will stop here for today, and next time I'm planning on giving one thing that I will do is the equivalence between this definition of property T and actions on median spaces. And since we talked a lot about quasi-isometry invariance, I'd like to mention that property T is not a quasi-isometry invariant. Anti-T is not a quasi-isometry invariant. Amenability is a quasi-isometry invariant. And I'll give all those examples, and I thank you for the attention.
Are there any questions?
Any greater or equal to 3 is open? Oops. Right, they did it first for 5, and then somebody got smarter and did 4, and so 2 is false, right? So it doesn't have, but is it AT amenable? Somebody knows? 2 is virtually free. 2 is virtually free. So, oh, it's virtually free, so it's here. Is that here? Out of 2 is here. Well, it's SL2Z, right? Okay. GL, well, okay. In this world, they're equal, right? Okay. So N, oh, okay. So N, so out of 3. So you're saying that's, and so it's mod for surface of genus, I think, well, surface of genus 1, it's SL2Z. We know they don't have property T. Genus 2, I think it's known-ish that they don't have property T, but I don't really remember why. And I think it's open for G greater or equal to 3. I'm not sure. I'm not totally sure of myself here. Sorry? Yeah, but I think that I think that for genus 2, you surject on some F2 cross F2, and I think that would kill property T. All right, so right, let me just not say anything useful. Yes. Yeah, no, the median space, the actions, the median space action for a amenable group, I don't understand it at all. Yeah, yeah, the action is proper, but if you look at the orbits, I don't know, the orbits are not quasi-isometrically embedded or not quasi-convex. Yeah, I don't know. I really don't understand this. It exists out of some kind of theoretical way, which has no geometrical meaning to me. It kind of does construct a space, but it's not construct in the sense of we geometry would like to say construct, because you kind of see all the pieces. Yeah. I have no idea. I have no idea. I mean, there's this 3-page paper, which I actually had never really read before, like 2 years ago. When I had to prepare a talk on property T. And I was like, okay, yeah, this big 1,000-pages book is a bit too long for me. Let's go for the 3-page paper. So yeah, I mean, I don't know how he came up with it. I don't know, do you know? I mean, who knows? He was 17. You don't never know what those 17-year-olds come up with weird stuff, right? No, he was really, so I think he was really doing it for SLNR. And that was really the question. Are those lattices all finitely generated? And he said yes, because, so what he said really is yes, because he showed that all semi-simple Lie group in higher rank, I think maybe he did it for simple Lie group, all Lie group of simple rank greater than 2 have property T, and then he shows that property T is inherited by lattices. It goes from lattices to the Embrand group and vice versa, and then that, and that's it, right? Yes, teenage angst, I think.
Yeah, any other questions? Okay, let's thank the speaker again.